In this question, a scientist has a sample of a 0.582 molar solution of a fictional weak base, M2A, at 25 degrees C. So here's our equation. We have M2A, and it combines with water and dissociates into the ions M2AH plus and OH minus. We're also given the base dissociation constant Kb for this equation is 3.84 times 10 to the power of negative 10. Okay, let's start by finding an expression for the base dissociation constant. Let's head to our reference sheet. Here's our expression for the base dissociation constant. Kb is equal to the concentration of hydroxide ions times the concentration of our conjugate acid, Hb+, divided by our base, B. Okay, so this is our equation, but the B represents a general base and the BH plus represents a general conjugate acid. We can put in the formulas for our specific base and conjugate acid from our question. Our base is M2A and our conjugate acid is M2AH plus. So let's fill those in. So for OH minus, it's just still OH minus. For BH plus, that's our conjugate acid, which in this question is M2AH plus, divided by the concentration of our base, which in our question is M2A. So there's our base dissociation constant equation in terms of species from our chemical equation. So let's go ahead and fill that in here. We've got OH minus and M2AH plus. The order doesn't matter, it's the same thing since we're multiplying. On the bottom, we've just got M2A. Awesome, okay. Next, we're gonna complete the ice table for this base. Again, this is gonna happen exactly the same way as all the other ice tables we've done. So we're gonna start by filling in our known initial concentrations. So we know we have a 0.582 molar solution. So that's going to be the initial concentration of our base, M2A. For our conjugate acid and our hydroxide ions, it's going to be 0 initially. So this is initial is kind of before it dissociates. The equilibrium will be when it's dissociated, and the change is how much change we have between those two times. So for the change, we're going to write it in terms of a variable x. We're going to look at our equation up here and see how much of each thing would get used up or made. So if we use up X of M2A and we use up X of H2O, that's going to produce X of M2AH plus and X of OH minus. So we have a change in concentration of negative X for M2A and a change in concentration of plus X for M2AH plus and OH minus. H2O is a liquid, which is why it doesn't appear in our table here, because the concentration isn't changing. Even if it gets used up, because it's a liquid, the concentration is constant. Okay, so now a formula for our equilibrium concentrations. All we need to do is add together our initial and change. So it's going to be 0.582 minus X. For M2AH plus, it's just going to be X because 0 plus X is just X, and the same for hydroxide. So those are our equilibrium concentration expressions. Now, there's one more thing we're going to do here, which is we're going to use the small x approximation. Which basically says that when we're adding or subtracting a really small x from a bigger number, it has no effect on the bigger number overall, because it's so much smaller. So that means that here, where we have 0.582 minus x, the x is barely going to affect this number overall. So we're just going to say that the x has no effect and it's just 0.582. Our next step is going to be substituting our equilibrium concentrations and our Kb given in the question into the Kb expression to calculate what x is. So Kb, we were given in the question, is 3.84 times 10 to the power of negative 10. OH minus, we have that as just X in our equilibrium concentration row. M2AH plus concentration we also have as X. And then on the bottom we have the concentration of M2A, which is 0.582. Let's write this out again, except I'm going to combine my X times X to make X squared. Then I'm going to multiply by 0.582 on both sides to get rid of that. On the right-hand side. And finally, I'm going to need to square root both sides of my equation to get X is equal to the square root of 0.582 times 3.84 times 10 to the power of negative 10. So let's go ahead and put that in our calculator. That gets me an X of 1.49 times 10 to the power of negative 5 molar. So we've got a very small change there as we expected, based on the fact that our Kb is really small. That means not much of our base is actually dissociating to form its conjugate acid and hydroxide ions. Okay, so now that we know X, we can go ahead and fill in our change in concentration and equilibrium concentration rows in our table. For the change in concentration of our base, it was negative 1.49 times 10 to the power of, which is written as E on this platform, negative 5. And for our conjugate acid, it's 1.49 times 10 to the power of negative 5. And the same for hydroxide, 1.49 times 10 to the power of negative 5. Awesome. Okay, then we need to fill out our equilibrium concentration row. Now, we made the small x approximation, which was that 0.582 minus x wasn't going to have any effect on our number. We can test that now in our calculator. If we do 0.582 minus 1.49 times 10 to the power of negative 5 and put that in our calculator. If we round our answer to 3 significant figures, we still get 0.582. So that's showing us that our small x approximation made sense. It was sensible to do that because our x didn't affect our initial concentration to 3 significant figures. So we can go ahead and fill that in here. And we can fill in our equilibrium concentrations here, which are just going to be the same as the change. Awesome. Okay, so that's our ice table complete. Next, we want to find the percent ionization of M2A in this solution. So let's head to our reference sheet. Percent ionization for a base is 100 times the concentration of the conjugate acid divided by the concentration of the base. Now B just represents a general base, and HB plus just represents a general conjugate acid. So we can put in our actual base and conjugate acid from the question. Our conjugate acid was M2AH plus. And our base is M2A. So we can put our numbers in. 100 times the concentration of M2AH plus at equilibrium is 1.49 times 10 to the power of negative 5, divided by the concentration of M2A at equilibrium, which is 0.582. That gives us a percent ionization for our base of 0.00257%. So we can fill that in down here, 0.00257%. Again, that makes sense. We have a really small percent ionization, which means that not much of our base was converted into its conjugate acid and hydroxide ions. And that matches up with our Kb, which is a really small number, times 10 to the power of negative 10, way smaller than 1, meaning our reactants are very much favored equilibrium. So that all matches up logically. Finally, we need to find the pOH and pH of our solution at 25 degrees C. Let's head to our reference sheet. Firstly, we have our pOH equation here. pOH is negative log the concentration of OH minus. Then if we want to find our pH, since we know we're at 25 degrees C, we can use this equation here. pH plus pOH equals 14 at 25 degrees C. So pOH is negative log the concentration of OH minus. So let's go ahead and put in our numbers there. pOH is equal to negative log the concentration of OH minus at equilibrium is 1.49 times 10 to the power of negative 5. So if we put that into our calculator, that's going to get us a pOH of 4.83. Let's check that. Awesome. So our last step is finding our pH from our pOH. So we're going to use the pH plus pOH equals 14 equation. We're going to subtract pOH from both sides so that gets cancelled out. And then we're going to put in our numbers. 14 minus pOH, which was 4.83. That gets us a pH of 9.17. So let's go ahead and fill that in over here now. Awesome. So to summarize, in this question, we're provided with the concentration and the dissociation constant for our acid or base. So our first step is to use our dissociation constant expression along with our ice table to figure out our equilibrium concentrations of each species. We can then plug in our concentration of H plus or OH minus to the pH or pOH equations to figure out our pOH and our pH. Remember, we're using the small x approximation, which means that when we're adding or subtracting x from a larger number, we're going to say that the answer is just equal to the larger number. We're going to ignore the effect of the x because it's so small, it barely makes any difference.